This is the 20th video in our series on Lie algebras. And in the past several videos, we followed the outline of starting with L, which we said was a finite dimensional complex semi-simple Lie algebra, taking L and finding its set of roots, which we called phi, and then we also looked at the real span of that set of roots, which we called E, and that became a real inner product space. And starting now, we essentially want to reverse that process. So we'll abstract a lot of the results that we saw in the above outline into something called a root system of an inner product space. And then, well, not today, but moving forward, we'll use root systems to construct finite dimensional complex semi-simple Lie algebras. So we really are reversing what we did in the last previous videos. Okay, so necessarily we'll need the definition of a root system, and here it is. So R, which is a subset of E, and E is a real inner product space. So this R is called a root system of E if it satisfies these four axioms. So first of all, 0 is not contained in R. R contains only finitely many elements, and the span of R is E. Notice I'm not saying that R is a basis for E. In fact, most of the time, R will not be a basis for E. And I'm just saying that it spans E. Then the second axiom says that if alpha is in R and C times alpha is in R, then C is equal to plus or minus 1. So in other words, the only multiples of roots that are inside of R are, well, the positive multiple or the negative first multiple. Okay. And then next, if we've got two elements of R, alpha, beta, then this angle bracket beta alpha, which I'm defining to be 2 times the inner product of alpha and beta over the inner product of alpha and alpha, is an integer. And then finally, if alpha is in R, we can define this map, which is, well, it's going to be the reflection of the inner product space about, or maybe I should say through, the hyperplane that is normal or orthogonal to R. And algebraically, it's defined as follows. So it's going to be beta minus this angle bracket beta with alpha in the alpha direction. And the important thing is that this map is a permutation of the elements of R. Okay, great. So we're going to start with the following observation, and that is if we have phi, which is a set of roots for a Lie algebra with all of those characteristics that we've been working with, complex, finite dimensional, semi-simple, then phi is a root system for, well, the real span of phi, which we called E before. Now, of course, this is something that we should have to be true because this definition down here is really just an abstraction of the phi that we looked at before, that set of roots. Okay, so let's go through these one at a time. So let's recall how phi is defined. So that's going to be all alpha in H star, where H is the Cartan subalgebra, such that alpha is not equal to 0 and L alpha is not equal to 0 also. But observe that this alpha not being equal to 0, that immediately implies that 0 is not inside of phi. Okay, but then let's also notice that if we take the size of phi, the cardinality of phi, by the root space decomposition of the Lie algebra, we'll see that that's equal to the dimension of L minus the dimension of H. But that's clearly going to be finite because L is a finite dimensional Lie algebra and H is a subalgebra. And then furthermore, by definition, we know that the span of R, or the real span of phi, is equal to E. Okay, great. So now let's move on to this second thing, which says that if alpha is in R and a multiple of alpha is in R, then that multiple is either plus or minus 1. But I'm just going to put a done here because that's something we proved before. Okay, nice. And now let's move on to this third one, which requires a bit of a calculation. So let's observe that if we do angle bracket beta with alpha, so by definition, that's going to be 2, and then the inner product of beta with alpha over alpha alpha. But then let's recall how those are defined. So this beta with alpha, these inner products are defined in terms of the inner products of those T alpha elements that came from the Lie algebra. So in fact, what we have here is that this turns into 2 over kappa T alpha times kappa of T beta T alpha. Okay, great. But now we can put this together a little bit, and what will we have? Well, we'll have kappa of T beta, and then we'll have 2T alpha over kappa T alpha T alpha. So that's just using the bilinearity of the Killing form. But now let's recall that this thing right here in the second entry was H alpha. So here we have kappa of T beta with H alpha. But then let's recall that T beta was the unique element of H satisfying the following condition, and that is that this is equal to beta evaluated at H alpha. But then beta evaluated at H alpha is an eigenvalue of the adjoint action of H alpha, and so that means that this is inside of Z. And that's because the eigenvalue of that adjoint action is integral by stuff we proved before. So let's maybe write that down. So this is, like I said, an eigenvalue of something we get when we take H alpha with something else. Okay, nice. So now let's move on to this fourth condition, which is the permuting of the elements of R. Okay, so let's maybe just do an S alpha beta and see what we get. So that's going to, by definition, turn into beta minus 2 inner product of beta alpha over alpha alpha in the alpha direction, where I just inserted, instead of these angle brackets, the definition of the angle brackets right here. But then a previous result showed that that was also a root. So there's nothing else to do there because, again, we proved that earlier. Okay, let's move on. Okay, so for our example, let's consider the following inner product space. And what's the inner product here? Well, it's just going to be the dot product on Rn plus 1. And this inner product space is defined as follows. So it's going to be all vectors of the form C1 epsilon 1 plus C2 epsilon 2 all the way up to Cn plus 1 epsilon n plus 1. But those coefficients, C1 through Cn plus 1, must sum to 0. And I guess I should say that epsilon I is the column vector where you have zeros in all of the entries except for the ith entry where you have a 1. So it's the standard basis vector. But let's observe that that's simply the null space of this maybe row matrix with all 1s in it. Okay, great. So now let's let R be the difference of 2 of these standard basis vectors. So in other words, epsilon I minus epsilon j, as long as I is not equal to j. And what we'll do is show that this is in fact a root system of E. So let's just go through these axioms over here. So let's see, 1. Well, 0 is not inside of R. That's pretty clear because we're assuming that I is not equal to j. And then what about this next one? R contains finitely many elements. Well, yeah, it most definitely contains finitely many elements, just based off of the fact that you can only choose I and j from the numbers between 1 and n plus 1. And then, well, the span of E is R. Well, that's pretty clear. You can maybe easily show that via a standard linear algebra exercise. We're not going to do that here. So for this first one, I'm just going to put a check mark. We talked our way through it. So now let's look at this second one. So if a multiple of a root is inside of R, well, then that multiple is plus minus 1. Well, that's pretty clear also just by the definition of R. So I'll put a check mark right there as well. Now let's look at this third one, and that has to do with this angle bracket right here. So let's take the angle bracket of this epsilon I minus epsilon j with, let's say, epsilon k minus epsilon L. So that's defined to be 2, and then the inner product of epsilon I minus epsilon j with epsilon k minus epsilon L over, well, we've got this inner product of, let's see, the epsilon k minus epsilon L with itself, which you can pretty easily calculate to be 2. So observe that those 2's cancel. And then, well, what are you going to be left with? Well, the dot product of epsilon I with epsilon k will give us delta ik. And then similarly, we'll have minus delta IL, and then minus delta j k, and then finally a plus delta jl. But notice that that's just a combination of ones or zeros. So pretty clearly, you're going to get an integer there. Okay, nice. So now let's look at this fourth one about this reflection about the hyperplane being a permutation. So let's look at S alpha of beta, where you'll see the definition of alpha and beta as we do the calculation. So this is going to be epsilon k minus epsilon L. So that's like playing the role of beta. And then minus, well, we're going to do this angle bracket of beta alpha in the alpha direction, but we calculated that angle bracket in this third part. So that's nice. We can just bring that down. So it's going to be minus delta ik, and then inside of that, delta il minus delta jk, and then plus delta jl will be that last one. And then this is in the epsilon I minus epsilon j direction. Now, there's going to be a bunch of cases here to check based on the choices of I being equal to k or not equal to k, and then so on and so forth. So let's just do one of the cases, and that is the case when I is equal to k and all others are not equal to each other. And then, well, all the other possible cases are essentially the same here. So let's see, we're going to get epsilon k minus epsilon L, just bringing that down. And then after that, we're going to have a minus, and then, well, all of these are going to collapse, and this is going to give us a 1. And then we'll have epsilon I, but I is equal to k, so we'll have epsilon k, and then plus epsilon j. So notice we get some simplification there, and that's going to give us epsilon j minus epsilon L, but that is an element of R. Okay, so there we have it. Okay, so now let's keep going. Okay, so for our next result, we'll suppose that R is a root system, and we have two roots alpha and beta, where beta is not equal to plus minus alpha. Then the only possibilities for angle bracket alpha beta times angle bracket beta alpha is 0, 1, 2, or 3. Okay, nice. So let's get to it. So let's just do a straightforward calculation. So we have alpha beta times beta alpha. So what's that going to be? Well, I'm going to use this definition down here. So this is going to give us 2 inner product of beta alpha over inner product of beta beta times 2 inner product of alpha beta over the inner product of alpha alpha. So I just used this definition down here for our angle bracket bilinear form 2 times. But now let's notice that this is simply equal to 4 times the inner product of alpha beta over the length of alpha times the length of beta all squared. And that's because, well, now it's a symmetric bilinear form, and that means that beta alpha is the same thing as alpha beta, whereas the angle bracket is not symmetric. You could have alpha beta not equal to beta alpha inside of the angle brackets. Maybe I should have pointed that out, but I think it's pretty clear by the definition right here. But now let's notice that this thing that's being squared is the cosine of the angle between these two root vectors. So this is going to be equal to 4 times the cosine squared of theta, where I'll put theta sub alpha beta here just to point out that that's the angle between alpha and beta. Okay, but cosine squared is always between 0 and 1. And so 4 cosine squared is always between 0 and 4. So this is between 0 and 4. But then furthermore, up here, we know that angle alpha beta and angle beta alpha are both elements of the integers. So that means their product is also an element of the integers. So this is also intersected with the integers. So we have the interval from 0 to 4 intersected with integers, but pretty clearly that's going to be the set 0, 1, 2, 3, 4. And now all we have to do is explain why it cannot be equal to 4. So if we have alpha beta times beta alpha equal to 4, then, well, what does that tell us? That tells us that theta is equal to 0 or theta is equal to pi. That's because in this case, cosine squared is equal to 1, and cosine squared is equal to 1 at 0 or an integer multiple of pi, but we might as well just take the angle to be 0 or pi. But notice if theta is equal to 0, then that implies that beta is equal to alpha. And that's because that means they're pointing in the same direction. But by this rule right here, if they're pointing in the same direction, then they're the same. But then over here, this means they're pointing in opposite directions. But again, using the same rule, that means that beta is minus alpha. But both of those are things that we assumed not to be true. So that gives us a contradiction telling us that we cannot have 4 here. So scrubbing 4 away from this possibility leaves us with the result that we want. Okay, so now let's see where we can go from there. So here's something that immediately follows from that last lemma. So recall that the product of alpha beta with beta alpha was 0, 1, 2, or 3. But that means individually the possibilities for alpha beta and beta alpha in angle brackets are 0, plus minus 1, plus minus 2, and plus minus 3. And now what we'd like to do is relabel alpha beta if necessary, so that the length of alpha is less than or equal to the length of beta with respect to the original inner product. But then via a quick calculation based on the definition of this angle bracket bilinear form, that tells us that the absolute value of the angle bracket beta alpha is bigger than or equal to the absolute value of the angle bracket alpha beta. And from that, we can build this chart of all possible values of, well, those two angle brackets and the angles and stuff. So for instance, if the angle between these two roots is pi over 2, then these two quantities are equal to 0. But that's pretty clear because in that case, you get this inner product of alpha beta here. But the inner product of two things that are perpendicular is always 0. Then if the angle is pi over 3, between these two angle bracket things are 1. If it's 2 pi over 3, you get negative 1. If it's pi over 4, for alpha beta you have 1, and for beta alpha you have 2. For 3 pi over 4, you have negative 1 and negative 2. For pi over 6, you have 1 and 3. And for 5 pi over 6, you have negative 1 and negative 3. And now let's observe that in these cases as well, you get longer and shorter roots. Notice in this case, the ratio of the length of beta and the length of alpha squared is 1. So those two roots have the same length. And when I say length, I mean with respect to the original inner product. But in this case, where the angle is pi over 4 between them, or 3 pi over 4, you have one that is longer. I guess it's the square root of 2 longer. And the same thing down here when you have angle pi over 6 or 5 pi over 6. Now, we've got a proposition here that follows pretty quickly from all of this, and that says that under this setup, if your angle is bigger than pi over 2, then alpha plus beta is also a root. And if the angle is less than pi over 2, then alpha minus beta is a root. So this is pretty straightforward. Notice that if, in this first case, if alpha beta is bigger than pi over 2, then, well, what do you have? Well, you have S beta alpha. We know that that is an element of R, but then that's also equal to alpha minus the inner product of, I shouldn't say inner product, the bilinear form of alpha with beta, beta. But then notice that in all of those cases, when theta is bigger than pi over 2, you get angle bracket alpha beta is -1. So that turns into alpha plus beta. But like I said, that is for this first case. And then that second case is very, very similar. So in this second case, you'll have that this S beta alpha is inside of R, but then that's also equal to alpha minus beta for the same reason, because notice that you'll get a +1 in all of those cases. Okay, so we're going to finish this video off with a classification of all two-dimensional root systems. Okay, so for this last example, we're going to, like I said before, classify all two-dimensional root systems R. So R is a two-dimensional root system. But it being a two-dimensional root system means that it spans R2. Well, that's what 2 dimensions would mean. But that means that there must be 2 linearly independent roots. I'll call them alpha 1 and alpha 2. And then after that, I'm going to choose alpha 1 so that the length of alpha 1 is less than or equal to the length of any other root. So it's the shortest root, if you will. And remember, all of this length stuff is in terms of the original inner product, not the angle bracket thing. If you observe, the angle bracket of any root with itself is always equal to 2. So that's not a good measurement for length, if you will. Okay, then next up, we're going to choose alpha 2 so that the angle between alpha 1 and alpha 2 is bigger than or equal to pi over 2. And you might say, well, how can we do that? Well, if the angle is less than or equal to pi over 2, we can simply exchange alpha 2 with negative alpha 2, and well, then we'll end up with an angle that's bigger than pi over 2. And then, well, in terms of that, replacing it with the negative, let's notice that you can always really do that, and that's because if you reflect any root through the hyperplane that is normal to that root, then you get negative that root. But that means that if alpha is a root, then negative alpha is also a root. And then here's a portion of that chart that we built last time just based off of this assumption that we've got an angle bigger than 90 degrees here. So notice our possibilities are both of these angle bracket alpha 1 with alpha 2 and alpha 2 with alpha 1 is 0. We could have -1, -1, -1, -2, -1, -3 with these corresponding angles. And then, well, how do we build up the rest of the root system via these, what I'll call simple roots? That's essentially what we're going to call them later. Well, we do it by, well, essentially just doing all possible S alphas or reflections through hyperplanes until we create a closed system. Okay, so let's start right here with our angle being equal to pi over 2. But that means that these two roots are at 90 degrees from each other, or make a 90-degree angle with each other. But notice that means that, well, I mean, we're like essentially done. Notice that if we take the hyperplane, which is just a line in this case, that's orthogonal to alpha 1, well, that's going to be parallel to alpha 2. And if we do a reflection, it'll take alpha 2 to itself and negative alpha 2 to itself as well. So this plus minus alpha 1 plus minus alpha 2 is closed under doing all those reflections. So that makes this the entire root system. Now in these other cases, I've started with my alpha 1 and my alpha 2 and the angle between them. And from that, we'll build the rest. Okay, well, let's notice that here we've got the angle between them is 2 pi over 3. But then by that previous proposition, if the angle between them was 2 pi over 3, then from there we knew that their sum was also a root. So that tells us that for our root system, we at least have plus minus alpha 1, plus minus alpha 2, and then plus minus their sum. We get their sum because of that previous proposition, because again, the angle between them is bigger than or equal to pi over 2, or bigger than pi over 2. And then we get negative from this observation right here, I guess it is. But now let's put that in there. So this alpha 1 plus alpha 2 will be in this direction. And then, well, since these roots have the same length, it'll be exactly between them. And then negative alpha 1 minus alpha 2 will be in this direction. So here is alpha 1 plus alpha 2, and here's minus alpha 1 minus alpha 2. And then, well, from here you can check that this is also closed under all such reflections, making this a complete root system. Well, a complete two-dimensional root system. And now let's move on to this next one where the angle is 3 pi over 4. And in that case, these roots have different lengths. And we've set up alpha 1 so that it's the shorter one, and notice that this is shorter than this right here. Okay, great. So now let's do some calculations. So let's notice that if we do S alpha 2 applied to alpha 1, well, we're going to get alpha 1 minus the inner product of alpha 1 with alpha 2 in the alpha 2 direction. That turns into alpha 1 plus alpha 2. So that means that, well, their sum is a root. I guess we already knew that from the previous proposition. But now let's do one more. Let's do S alpha 1 applied to alpha 2. So that'll be alpha 2 minus the inner product of alpha 2 with alpha 1 in the alpha 1 direction. That turns out to be 2 alpha 1 plus alpha 2, because this alpha 2 alpha 1 is negative 2. So that means this sum, alpha 1 plus alpha 2 and 2 alpha 1 plus 2 alpha 2 are also roots. And you can find their length as well, and you'll notice that the first one is shorter than the second one. So let's put our alpha 1 plus alpha 2, so that's going to be right here. So geometrically, we know that it's going to be orthogonal to alpha 1, just based off of the fact that it's alpha 1 reflected through the line that's orthogonal to alpha 2. So let's put here, this is alpha 1 plus alpha 2, and then I won't label the bottom, but that's in the negative direction. Okay, and then what about the next one? Well, that's in fact going to go in the middle right here, and you can see that from the geometry of this whole situation as well. Okay, so let's get that drawn. This is going to be 2 alpha 1 plus alpha 2. And then that completes a root system in this case. So here you have plus minus alpha 1, plus minus alpha 2, plus minus alpha 1 plus alpha 2, and then finally plus minus 2 alpha 1 plus alpha 2. Great. And then, well, like I said, that completes everything. Okay, so now let's move on to the last case where the angle is 5 pi over 6 between these two roots. Let's go ahead and start off down here what we know. So we know that R will contain plus minus alpha 1, plus minus alpha 2, and then plus minus alpha 1 plus alpha 2. Again, that proposition tells us that since the angle between them is bigger than pi over 2, their sum is also a root. But now let's do some other little calculations. Let's do S alpha 1 in the alpha 2 direction. And I won't write out the definition here, but what you end up with in this case is 3 alpha 1 plus alpha 2. Okay, and then it turns out that if you do, let's see, S alpha 1 applied to alpha 1 plus alpha 2, you end up with 2 alpha 1 plus alpha 2. So that gives us, well, it gives us 4 more roots, those two and their negatives to put in here. So let's see, we've got plus minus 2 alpha 1 plus alpha 2, and then plus minus, it's 3 alpha 1 plus alpha 2. And then there's actually going to be one more, and we get that from doing I'll put that in down here, S alpha 2 applied to 3 alpha 1 plus alpha 2. And you end up with 3 alpha 1 plus 2 alpha 2. And that's going to be our last root down here. So plus minus 3 alpha 1 plus 2 alpha 2. Okay, so that's our complete root system in this case. And now all that's left is to make the picture. And what you end up with is the following. So this is a little bit tricky, but this root right here will be our 3 alpha 1 plus 2 alpha 2. And then you've got 1 in the middle of these two, which turns out to be alpha 1 plus alpha 2. And then the remaining two are fit in the middle right here. Okay, so let's see which one goes where. So this one is going to be 2 alpha 1 plus alpha 2, and then this one is going to be 3 alpha 1 plus alpha 2. And then that would be our complete root system in this last case. And that's going to be all possible two-dimensional root systems because we've gone through all possible angles between these two roots. And that's a good place to stop.